Good morning, everyone. Today we will be presenting CPU design, performance, and parallel processing. My name is Devmit and our group members are Dinuga, Mitsani, and Purindada. We will cover five major areas: computer structure, system performance, CPU function, and advanced CPU concepts, and Flint's classification as well. For the table of contents, we will discuss what basic structure of a computer system, basic performance in a computer system, CPU functions, advanced CPU functions, and parallel processing. Please classification SISD, SIMD, MIMD, and SPMD as well. Now, next, I'd like to invite Dinu.
Thank you, Devmit. And let's talk about a computer system consists of four main function units. They are input unit, output unit, memory unit, CPU. The first one is input unit. Receive data user commands. Output unit is shows the processing information. Third one is the memory unit. Store instructions and data include RAM and secondary storage. CPU. The main processing unit containing the ALU is the arithmetic and logic unit operating system. Control unit is the coordinating all the activities. The next slide is the processing cycle and data transferring. The computer process data through the four steps. The first one is input, second one is process, third one is output, fourth one is storage. The in the set CPU fetch, decode, execute cycle to the run instruction. Fetch is control the unit retrieving the instructions from the memory. Decoding is install the all the instruction in the register. Execute is the ALU carry out the operating. The third line is the data bus moves between memory and the CPU through the bus line. The first one is address bus line, second one is data bus line, third one is control bus line. Now I hand over to the Mitsarni. Thank you.
Thank you, Dinuga. Now I will explain two important computer architectures. First one is the von Neumann architecture. In this system, instructions and data use the same memory. Because of this, the computer can read only one thing at a time, and this slows down performance. This problem is called the von Neumann bottleneck. Next is the Harvard architecture. Here, the computer uses separate memory for instructions and data, so it can access both at the same time. This makes the computer work faster. There are also three main things that affect computer performance. First is the clock speed. Higher clock speed means the computer can do more cycles per second, so the computer works faster. Second is the cache size. Cache is a small and very fast memory inside the CPU. A bigger cache helps the computer read data faster. Third is the number of cores. More cores mean the computer can do many tasks at the same time. This improves performance through parallel work. Now I will hand over to Purinder, who will explain the processor design steps.
Thank you, Ms. Sani. Now I'll explain the main steps involved in designing a processor. The first step is requirement definition. Here we decide what the processor must achieve, its performance, power usage, cost, and the type of device it will be used in. The second step is selecting the instruction set. This is the basic language of the processor, choosing an ISA like ARM into 86 or RAIC-V. Next is building the data path and control unit. The data path includes the ALU, registers, and buses. This is where operations happen. The control unit sends signals that tell each part what to do. Together, they form the working core of the CPU. Finally, we have implementation and testing. Engineers simulate the design, check for errors, and verify that the processor works exactly as intended before manufacturing. And next slide. Now let's look at the types of instructions a CPU can execute. The instruction set defines the operations of the processor can perform. The main categories are data transfer instructions like load and store. They move data between memory and registers. And arithmetic instructions such as add and sub. These perform calculations, and logical instructions like AND and OR used for bit level operations and decision making, and the control flow instructions like jump and branch, they change the sequence of execution, and input and output instructions which allow communication with external devices. And a well-designed ISA includes a balanced set of these instructions to make both hardware and software efficient. Thank you. Now I hand over to Ms. Rani.
Thank you, Purinder. Now I will talk about three CPU design methods. The first one is the single cycle processor. Here every instruction finishes in one long clock cycle. It is simple, but it is not very fast. The second one is pipelining. In pipelining, the CPU breaks an instruction into stages: fetch, decode, execute, memory, and write back. Many instructions can be in different stages at the same time. This makes the CPU faster. The third one is the superscalar processor. This type can run more than one instruction in one clock cycle. It uses many functional units in parallel, so it gives higher performance than a normal processor. Now I will hand over to Devmit to explain Flint's classification and the real-world examples.
Thank you, Ms. Sarani. Now I'll explain about the Flint's classification groups and system based on instruction and data stream. First one is SISD, which is single instruction, single data. For example, basic uniprocessor. Second one is SIMD. It is a single instruction, multiple data process. It's mostly used in GPUs and vector processors. The third one is MISD, multiple instruction and single data. These are very rare and used in specialized systems. The fourth one is MIMD, multiple instruction, multiple data. It is a multi-core processors and clusters. And we have SPMD, which is single program, multiple data. This is a programming model often used on MIMD systems. Now let's talk about the real-world examples. Real-world examples include for SISD, single-core desktop CPUs. For SIMD, graphics processing units. For MIMD, multi-core CPUs and cloud clusters. For SPMD, parallel applications using MPI in high-performance computing. These architectures show how different systems handle parallel tasks efficiently. That's all for today. Thank you. For the conclusion, I'd like to tell that computer systems operate through structural and functional units. Performance depends on architecture, instruction set, and parallel features. Advanced concepts like pipelining and superscale execution significantly boost CPU throughout. Flint's classification helps us understand parallel computing systems very modernly. Thank you very much. Thanks for listening. If you have any questions, please reach out. Thank you.